Hi, my name is Ron Boring. I am your host or your introduction to this meeting today. Very pleased to have you join us today. Go ahead to the next slide there. And this is our Machine Learning AI Symposium, the fourth iteration. Again, this is a series put forward by the INL Nuclear and Science Directorate. I am the manager for the Human Factors and Reliability Department. And this is a topic, we'll get into this in just a second, this is a topic particularly of interest to the human factors community as well as many others. Next slide. So I mentioned this is the fourth of the series. The first three symposia all had slightly different focus areas. In April, we had our first AI machine learning symposium. We've since added big data. The first one really focused on internal to INL activities, and initially we actually just shared it internally at the INL. We had about 200 attendees at INL and realized that this was an area of huge interest, and we also had a lot of people who were interested outside of INL. So we extended the symposium beyond INL. Next slide there. In July of 2020, we had our second symposium, and in this one we engaged industry and universities. And one of the big takeaways from that, many good talks there, was that AI and machine learning will continue to be a key technology moving forward as we continue our research and development program at INL. And then we followed that up in October with the Symposium 3.0. And here we started focusing in a little bit more. We focused on nuclear-related applications using AI and machine learning. And one of the things about this is it really revealed that there was a rich collection of AI applications already underway to help with tasks like monitoring, risk prediction, and maintenance. Okay, next slide. And that brings us to Symposium 4.0, and we're narrowing it down even more, this time to talk about trustworthy and explainable AI. Now that's, of course, a huge topic in and of itself. But I think you'll find a couple themes here as I've previewed some of the talks that we'll be hearing today. And ultimately, the success of AI or machine learning or even big data depends on AI doing what it's supposed to do, so it needs to be reliable. And I think a lot of that topic was covered in the first three iterations of this symposium series. Next. And then we need to, the success of AI depends on us trusting that AI is doing what it's supposed to do. So that gets us to this trustworthy topic. And I know a lot of our speakers will enlighten you more on what trustworthy AI means. But basically, a system that does something we don't expect it to do is not likely to be invited to do it a second time. And that's especially true in many of the applications that we work in the safety critical industries. There's really no margin for AI surprises. And then the final point there is that the success of AI or machine learning or big data depends on us understanding what the AI is doing. And that's the explainable part of it. This is not completely independent of trustworthy AI. We really need to understand what it's doing before we trust it. Next slide. And so the common denominator in today's talks is that AI, machine learning, and big data are technologies ultimately used by humans. AI does not supplant the humans, it augments us. And we must be mindful of the end users of AI. That's something that I hope you will take away from today's presentations. Next slide. And so today we have 7 presenters giving short presentations on trustworthy and explainable AI. We'll start off with Matt. You can see him up there, Matt Turk from DARPA, who's going to give a little bit of an overview of explainable AI. Of course, DARPA is really the harbinger of much of this work, so we're very excited to hear from Matt. We'll next go to University of Tennessee at Knoxville, and we'll hear about explainable AI to support operations and maintenance in nuclear power plants. Again, we're coming from a nuclear background here, so it's always important to keep that connection. We'll next hear from North Carolina State, who's been doing a lot of work on digital twins and is looking at that trustworthiness aspect in using digital twins. And next, we'll go to Virginia Commonwealth, where they have been working a lot on trustworthy AI guidelines for human-system interactions. Next, we'll go over to Argonne, a good colleague of ours at our sister lab. Rick Phillum will be talking about improving explainable AI through process information and automated reasoning. We'll make a brief stop at INL to talk about reaction mechanisms with explainable AI. And finally, we'll stop over at MIT and we'll hear about neural networks for control of a subcritical facility. Now, before I introduce Nancy, who's really going to be the MC through this, I just want to very briefly acknowledge our previous symposium organizers, Curtis Smith and Craig Primer. And then we have a whole army of behind-the-scene helpers, including Erica Sanchez, who's driving the slides today, Eric Schuster, who's our go-to-meeting guru, and Sue Little and Christy Whitmill, who have helped organize all of this. So we want to give them a big round of applause. And without further ado, I will hand the time over to Dr. Nancy Liebeck, who's the manager for INL's Instrumentation, Controls, and Data Science Department. Thanks. And pull up some lunch and enjoy the show.
Hey, well, good morning or good afternoon, depending on where you are. And welcome to our 4th symposium. We're excited to get moving on this. So without any further ado, I will introduce our first speaker. So Dr. Matt Turek is a program manager in DARPA's Information Innovation Office. His research interests include computer vision, machine learning, artificial intelligence, and their application to problems with significant societal impact. And he's talking today on DARPA's Explainable AI program. So Matt?
Great, thanks for the introduction. As Nancy mentioned, I'm Matt Turek. I'm the program manager for the Explainable AI program at DARPA. This was a program that started in the spring of 2017. So it's a 4-year basic research type program. And it was started originally by Dave Gunning, who was the previous program manager at DARPA. So next slide, please. So let me frame up the problem space, or at least as DARPA saw it, for explainable AI. And certainly a lot of work has taken place since the program initially kicked off, both within DARPA, in our performer base, and outside of it. So that the area, again, has grown quite a bit. DARPA often thinks about problems in terms of where we are today, so that's the top part of the slide, and then where we're trying to go with the new program. So in terms of explainability, certainly when the program started, again, around 2016, 2017 timeframe, you can imagine the machine learning process illustrated on top, right? So you have some large amount of training data, it's probably labeled, it goes through some learning process to create a model, here labeled as a learned function. And so that's really, those few boxes are really the training process. And then the test process, you take a input image, so illustrated by that detecting ceasefire violations image on the top of the slide, that goes through your learned model, your learned function, and you get an output. In this case, you get a classification output. This incident is a violation, and maybe if you're lucky, you get a probability associated with that. And so the challenge from a user perspective is that they don't have a view into the model, into why that decision was made, right? So they really don't. Just providing that score and the probability value just doesn't provide sufficient information for the user to really build their confidence. And they don't understand when the model is going to be successful, when it's going to fail, and how they need to respond to what the model is producing. So the bottom half of the slide is where we wanted to go with the program. And in particular, things like new learning process. So again, maybe there's a large amount of labeled training data, but a new learning process that could produce a more explainable model. So it might be that there were innovations in the training process. It might be that there are innovations in the model structure itself, and I'll show you some examples of that. But also importantly, that there's innovations in something we called an explanation interface. So not just providing to the user the decision that this incident was a violation, but reasons why. And that's to support again, more transparency to the user, more understanding of why the algorithm made the decision it made. And ultimately, that's really in service to building more trust between the system and the user. So we focused on things like new learning processes, new model structures, and explanation interfaces. So next slide. And so again, we often have this today, tomorrow construct when we're putting together programs. And so one of the things that was in the let's say the community mindset about explainability is illustrated by that notional graph in the middle of the slide, which is labeled a performance explainability trade-off. And so certainly the thinking was at the beginning of the program that that there was this inherent trade-off between learning performance, so think of that as something like classification performance, and explainability. So things like decision trees, it's pretty easy for a user to trace through them, to understand why a decision's being made, where the, let's say, where the decision points are. But the learning performance is not equivalent oftentimes to something like deep learning, which can often be very opaque and nearly impossible for a user to really dig into and understand. And so the idea was to be able to shift this curve, this notional curve from deep learning through decision trees to the right, or perhaps to the up and to the right. And so to maintain learning performance, but to improve explainability. And one of the interesting things that we found on the program is that explainability can actually improve performance in some cases. And while that, I think originally at program formation time seemed counterintuitive, now we can think about it in terms of explainability and the process by which you build an explainable model, providing more supervision to an algorithm. So in some sense, more training data or forcing it to learn better representations that actually allow it to make better decisions. And so in terms of program structure, we focused on a few explainable strategies, interpretable models, deep explanations, and inducing models from existing, let's say, black box algorithms. And I'll talk a little bit more about those in future slides. Next slide. And we focused on really two problem areas at a high level, one data analytics, and the other is autonomy. So from a data analytics perspective, being able to explain a recommendation to an analyst, and autonomy, being able to explain actions to an operator. In the data analytics space, there's been quite a bit of focus on image and video type problems. So that's been the primary areas of effort in data analytics on the program. And then on the autonomy side, there's been a lot of work in terms of gameplay. Next slide. So one of the challenges in this space, and I think this is an important point to make, back to Ronald's comments about being user focused, is that there are different categories of users and they really need different types of explanations. So along the bottom of the slide, you can see a notional timeline that goes from conceptual system through developing prototypes and doing things like validation and verification and acceptance testing to operating a system. And then post operations, things like after action reviews and regulatory reviews. And on the top 2/3 of the slides, there's different categories of users that are really associated with those time points. So things like AI experts or subject matter experts for a particular task that are involved in the development process. They're really interested in trying to debug the system and its inner workings during development or into, let's say, the validation, verification, system acceptance testing time. From an operational perspective, obviously there's a need to understand particular decisions that a system is making or the recommendations that a system is making. But there's also the need to understand more generally how a system behaves, how it makes decisions. that starts to cross over from, again, system acceptance testing to things like training of users and to just having a general mental model for how a system operates that they can incorporate into their decision-making process when they're collaborating with an AI algorithm. And then on the policymaker and regulator side, they might want to look at a pattern of decision over time and see if that's defensible and in alignment with policy or regulatory requirements. So all these groups have very different needs for explanations. The program is focused primarily on that developers and the end users in terms of where we've invested the most of our effort. But we have done some work actually in terms of supporting policymakers and regulators, in particular with an after-action review process for AI systems. Next slide. So I hinted at this in terms of the discussion of users, but there's different categories of explanations as well. So we talked about these on the program in terms of global explanations and local explanations. So a global explanation is essentially how does the AI work generally? So if you can imagine a AI task like a autonomous submersible maneuvering to a target location, maybe the explanation is a description of the learned policy in general for how the AI deals with routing around friendly vessels. And then local explanations, again, those are explanations about a particular decision. And so here you could think about a data analytics task where you're trying to detect resupply activity at a military installation. And so the type of explanation might be appropriate there is specific to the data that's presented. And in this case, maybe pointing to the specific change that happened recently. And so both those explanation types are needed to help build a real mental model of the AI system. Next slide. Okay, so I'm going to give some examples of those high-level algorithm approaches, and then I've got a number of little vignettes of results from the program that we'll go through, and then happy to take questions. So at a high level, there's a number of strategies that we've invested in. So in terms of interpretable models, that might be a model representation that is easier for a user to dig into, that is more understandable, that can also provide the explanations of what's going on, but importantly maintains that same level of learning performance. So this is the illustration here is work being done in tractable probabilistic modeling. That's from UT Dallas. And that allows, enables the construction of a model that is more introspectable. So there's a essentially tree type representation for this tractable probabilistic model that has some inherent factorization of the constituent probabilities underneath it. And that basically is an OR graph type representation. And that allows for more transparency and more traceability. A lot of that is in service to developers. And then on the deep explanation, these are really modified deep learning techniques. So you can think about this as doubling down on deep learning approaches to produce explanations. So the example here is work done by UC Berkeley, where they're taking video as input to a self-driving car controller that's trying to estimate steering and velocity. And they are producing, in addition to the control signals, both a visual saliency map or a visual attention map for where the system is tending to in the scene, and a text-based explanation of the behavior of the system. So the car is driving forward here because there are no other cars in the lane. And so that's a combination of state-of-the-art machine learning models to both regress the control signals and to produce the explanations. And then model induction is trying to come up with a model that creates or approximates another model with a more explainable model. And so this is work done by Oregon State University to insert a quantized bottleneck network. So you can think about this as a quantized autoencoder that is inserted into a recurrent neural network at training time, and from which you can extract a finite state machine. And then you can go through various processes to convert that potentially very complicated state machine into a representation that's easier to interpret. And so they've explored approaches from minimizing that state machine to actually coming up with transformations that enable more explanation. All right, next slide. So now I'm going to show you a few example vignettes from XAI. So this is RISE, or randomized input sampling for explanation. So this is work done from the UC Berkeley team in conjunction with Boston University and Kate Sanko. And so what this work is doing is producing a visual saliency map for a black box image classifier. So in this case, the black box classifier takes in the image on the left-hand side and makes a prediction about what it thinks it's seeing in the scene. So in this case, it makes a prediction that this is actually a solar farm, which is incorrect. And then the next highest, probabilistically, the next rated result is a shopping mall. And what RISE allows you to do is take a look at where the network is attending to when it's making those decisions. And so when it's suggesting solar farm, it's paying most attention to the roof type structure, and perhaps there's a bit of specularity there that's catching its attention, versus the shopping mall, where it's really focused on entrances and exits around the edges of the building. And that is evident again from the heat map. And the nice thing about this again is that it works essentially with any black box style image classifier. And it works by basically randomly removing patterns of pixels in the input image, running that through the classifier, and then accumulating the attention maps, so you get a sense of where the network is paying attention. Next slide. This is work done by Rutgers University, and this is really explanation by example. So they've got a nice Bayesian teaching framework that they can use to optimally select from the training set examples that are similar to the image presented for classification as part of the reason for why they selected a particular class. So there's two test images shown on the top and bottom half of the slide. The top is essentially a bobcat image, and so the choice here is this image from category A or B? And in this case, the classifier would be recommending A, and that is based off the similar bobcat examples. Similarly, for doing something like spider classification, that is illustrated on the bottom half of the slide. So Rutgers has fleshed out a nice, again, Bayesian teaching framework for this approach that they are now applying to medical imaging type problems. Next slide. So this is work done by Raytheon BBN in conjunction with MIT, and this is really network dissection for things like AlexNet, and also has been applied to GANs. And so the idea is to combine both information from things like visual saliency maps automatically with object detectors that provide some idea semantically of where the network is focusing, and that allows producing the sort of visualization shown on the right half of the slide, where you can associate different layers and different nodes in the neural networks with different object categories, and understand how that evolves through the different layers of the network. Next slide. So one of the things that is interesting is that explanations can help particularly when the answer is wrong. So one of the ways that we have assessed a number of the algorithms on the XAI program, and really the gold standard for doing the assessment, is via detailed user studies. And those user studies have basically confirmed this idea that explanations in particular are useful when the answer is wrong. So you can think about that intuitively from the perspective of an analyst using a system. If that is a black box system, it's making decisions that you disagree with. If you have no understanding of why that decision is being made, you're probably going to lose trust in that system pretty quickly. If you have a sense of why that system is making decisions or what it's attending to, that may help you continue to maintain trust in the system, even when it's not producing answers that are correct or that you agree with. And so in this case, this is a visual question answering task, and the image illustrated on the left-hand side, that's the input. The question is, what city is this? The answer that is predicted is London, which you would quickly look at visually and perhaps quickly. If you're in the DC area, you may actually recognize that that bus runs nearby DARPA, and realize that that is actually not London. But it's particularly telling when you see the explanation and you understand that this misclassification really hinges on this incorrect understanding that this is a double-decker bus. Next slide. All right, and then one of the things that's been useful, again, in terms of the XAI techniques is really on debugging and improving our understanding of things like deep RL, deep reinforcement learning type algorithms. And so this is work done by Charles River Analytics in conjunction with some of their subcontractors, applying techniques to visualize relative values and estimates of reward for different changes to the game space. So this game here is very similar to Pac-Man. It's Amadar. And what was interesting that was discovered here was that the deep RL algorithms that were trained to play this game are actually quite weak to semantic interventions. So adding a new line segment or removing a ghost or an enemy from the board actually created significant errors in estimating the reward, and created significant errors in the ability for the system to play those games under those sorts of modifications. And so this was an example of where explainable techniques allowed the developers to really understand what was underlying the brittleness in the reinforcement learning algorithms that were being developed. And I think next slide is probably the end. So happy to take questions.
Hey, thanks, Matt. So for the audience, if you'll type any questions into the question box that you see on your screen, we'll convey in that way. And the first one comes from Roman Schaefer. Can the explanations be displayed in real time, say for video-based object detection?
So we have not really focused on the computational cost or the speed at which we've been producing explanations. We've really been focused on trying to develop the quality of the explanations. So I think that's a good question. But again, that was not really a focus of the program. One of the things related to that we did learn is that it is pretty easy to cause cognitive overload for a user by providing both an answer and an explanation. So you need to understand when the task is hard enough that it requires explanations, and that's ideally that would be something that you would do automatically. But really the state of the art is at least on the program, is taking that into consideration as you're developing the system and deciding whether you should provide an explanation.
Okay, great. Thinking of the user, what do you think is the most useful for them? Is it an explanation or a graphical display?
Yeah, I mean, that's a good question. And unfortunately, I think the answer is it depends. And it depends on the user, and it depends on what their task is and what background knowledge they have. So one of the things that was really, I don't know, was really useful for me to understand over the course of the program, or that I came to understand over the course of the program, was just how intimately tied the explanation is to the user. If you do not think about that carefully at design time, if you do not think about that carefully at evaluation time, you're likely to get pretty mixed results. As I mentioned, you can increase the cognitive burden, or when you do your user studies, you'll find out that your explanations don't actually improve things like task performance or their understanding of the system. So what that led us to is really the best practices are you really need to be engaged with folks that really understand user-centered design, that have some experience in cognitive psychology, because one of the other typical failure modes is when you set up your evaluation, and again, a user study is the gold standard for the evaluation. There are so many failure modes that you can fall into with your user study design. You really need someone who's quite experienced in doing that user study design.
Okay. All right, so a question from Edward Chin. It seems most explanation techniques are for classification tasks. For regression tasks without clear classification, like a temperature predictor, what are the additional problems there for providing explanation?
Yeah, that's a good question. We just really didn't work on regression problems that much. So I don't know that I've got a ton to say there. The closest, again, is a lot of the reinforcement learning type problems where you're trying to, estimate, where you're trying to estimate control signals and things like that. Those have different network structures. There were certainly things done to address that, but again, they require different explanation types, like the Oregon State work of trying to extract the state machine, or different ways to characterize and explain various reward signals or the trade-offs that an algorithm's making. Those were things that were focused on sort of in that RL space.
Okay, thanks. All right, let's see. From Raghu Sengwan, are there cases where users are not able to or find it difficult to validate an explanation offered by a system?
Yeah, I mean, it is, again, one of the lessons learned on the program, I think, is the difficulty of trying to assess the value of an explanation. There are things that you can pull from the psychology community. There are characteristics of an explanation that are known to be indicative of good style explanations. But again, it really depends on the task and on the user community. And that is why, at least the current state of the art is really to set up a detailed user study to understand the efficacy of an explanation approach.
Okay, so next question from Pradeep Ramahali. How do you reconcile the need to design the explainability up front with the user in mind and the different classes of users? In your spectrum of users you listed on one of the slides that may require different types of explanations.
Yeah, and I don't think we actually put together a comprehensive set of pieces that for a particular system spanned that entire life cycle. So that is certainly an interesting question. The reality is you just need different explanation types at those different time points. So for instance, those RL finite state machines are probably best used by the subject matter experts or the deep learning researchers to really understand what's being learned. Maybe they're appropriate for some users, but in reality, they're probably too complex for many of the users. And then they don't really get after policy type decisions. So, you know, there is no sort of universal explanation that's going to work for that entire user community.
Okay, great. So let's see, from Sun Tran, would an explanation about a reasoning process be useful?
Well, yes, I think in general, you know, again, it's going to depend on the task and the user. That explanation about the reasoning process might fit into that category of global explanations that I mentioned. So again, here's how a system might work generally as a global explanation. And so if you can provide to the user some context for how the system reasons generally, and maybe some examples that cover the sort of reasoning space, that's probably a useful approach, targeting things like user training or maybe broadly system acceptance tests.
Okay, well, we are at your 30 minutes here. So thank you so much, Matt. For the questions that we didn't get to, those will be passed on to Matt, and hopefully he'll be able to answer them for you. So thank you, Matt.
All right, thanks for the opportunity. Appreciate it.
Well, okay, so next up on our agenda is Dr. Jamie Coble. Jamie is an associate professor in the nuclear engineering department at the University of Tennessee, Knoxville. She investigates data-driven optimization of maintenance planning, detection and mitigation of human factors errors, integration of operational and health assessment digital twins, cybersecurity of digital INC systems, and data-driven monitoring of additive manufacturing toward part qualification. And Jamie's talking today about explainable AI to support operations and maintenance in nuclear power plants. So thanks, Jamie.
Thank you, Nancy. As Nancy said, I want to talk a little bit about the role of explainable AI in operations and maintenance, specifically for nuclear power, but I think a lot of what we see in nuclear power is true in other safety critical and high value assets. And so, you know, as we think about operations and maintenance planning for nuclear power plants, there's been a lot of research for decades now in optimizing maintenance planning, moving from the kind of time-based periodic maintenance to condition-based maintenance, and even really focusing that towards opportunities in nuclear power. But nuclear utilities have not taken advantage of that yet, right? And so we're not seeing a lot of shift from the current approach to inspection and maintenance activities to a more economic approach. And so I think that that's kind of where explainable AI and trustworthiness in AI can come in and actually fill that gap. So next slide, please. So for the folks who are familiar with the nuclear power world, this won't be any surprise, but you know, for a long time we've said that operations and maintenance costs are really our addressable costs in day-to-day operation of nuclear power. And so there are plants across the country and across the world that are shutting down largely due to economic reasons, not because they are unsafe or in poor condition by any means, but that they are not an economic power producer in their market anymore. And so, you know, studies suggest 60 to 70% of the day-to-day cost of producing electricity with nuclear power comes down to operations and maintenance, and maybe 80% of those costs are really attributable to humans. And so one of the big drivers that we look at as a way to mitigate those costs and to manage the costs is really considering how we do our periodic maintenance and inspection activities. And so right now in the US and in most of the power plants, inspection and maintenance of components and structures is largely driven by periods that were defined in technical specifications for the license for reactors. In our current fleet of light water reactors, we can kind of get away with that. We at least know how to set those periods because we have a long operating history. And so we know at least, during the first 40 to now 60 and even going up to 80 years of life, what frequency we need to do these inspection and maintenance activities to avoid in-service surprises. As we look at the next fleet of reactors, where we might have small modular reactors that are just a little bit different than our current light water reactors, or even advanced reactors that operate with different types of coolants and under very different concepts of operation, we don't have that operating experience to rely on to set those periodic activities. And so, basically the short version is that there are a lot of drivers for moving towards data-informed, data-driven decision making or decision support. And so, if we can automate the operations and maintenance planning for nuclear fleet, then we can manage some of these O&M costs and keep our nuclear power plants operational. So next slide, please. And so in nuclear power, for the most part, when we think about commercial reactors, we're not talking about the AI taking over and making all of the decisions and doing things on its own, similar to what they're doing in DARPA. We're really looking at support. We want to have decision support for operations and maintenance decision makers, whether those are the operators who are managing the day-to-day operation of the plant, or the engineers that are maybe planning when maintenance needs to take place and how it needs to take place. And so this really lets us move from human in the loop that we have in a lot of our O&M on nuclear plants right now, to human on the loop, so that the AI is providing a decision or a recommendation, and the human can either accept or not accept that recommendation. But if we just provide a recommendation without any reasoning behind it, then it's very difficult to decide that you want to accept that or not. And so that's really where the explainable AI or the trustworthy AI comes in, to allow the human on top of the loop to decide, should I trust this? Should I accept this decision? Especially if it maybe is outside of the bounds of what they've seen before, or the decision they would have made. And so we're really looking at what it would take to make an explainable and transparent system that provides to the decision makers the right level of information. So again, similar to what Matt was talking about with DARPA, is like, how do we get the right information to the decision maker on time so that they can make informed decisions. Next slide, please. And so the one of the approaches that we're taking at UT, and this is in collaboration with some of my colleagues in industrial and systems engineering, is looking at how we can build a framework around our AI decision makers that will model our trust or our confidence in the decision process, right? And so instead of just providing maybe a decision, or even a decision with a couple of pieces of evidence, we also want to provide a level of confidence in how much we should trust that decision. And so, we're looking at kind of a two-step or a two-model approach, where we have a model of our initial trust, or our kind of baseline trust, and then we can update that dynamically with our learned trust as the system operates, and as we get decisions from the system, and a human decides whether or not they want to accept that decision. We're looking at ways to incorporate that back into our trust model, so that we can adapt based on what's, not only adapt our decision maker, but adapt our model of how much we trust our decision maker based on the quality of decisions, the quality of evidence, how those things are communicated to the decision maker, and then what ultimately is done, what decision is ultimately made, and how that plays out in the system. Next slide, please. And so some of the opportunities that we kind of see to continue this type of development are really maybe domain-specific needs in continuing to develop artificial intelligence and machine learning tools that are appropriate towards, in this case, towards nuclear power plants. So we're looking at ways to mine information from the data that are already available at our power plants, whether those are process data, maintenance logs, things like that. We have a rich history of data, but it's not always transparent how to get into that data and how to pull information out of it. We're also looking at how to integrate some of this decision making with digital twins, which I think we'll hear about a little bit more next, but kind of looking at operational digital twins, health assessment and maintenance digital twins, and how all of those things talk to each other in a manner that is fast enough to make decisions. And then, you know, from a deployment standpoint, in nuclear, we have kind of two groups of people that we have to approach to deploy AI decision making. And so one group is the operator, the person that we're going to present a decision to, who would either accept it or not. So operators and engineers and planners. And so we're looking at ways to evaluate the reliability of the decision in real time. So again, that kind of model of trust, how much should we trust that decision? And then how are we going to display the right evidence at the right time to operators and engineers? How do we target the information that we're providing? And on the other side of it, we also have to convince the regulator that what we're doing is acceptable and makes sense. And a lot of that comes down to, you know, understanding the uncertainty in our decision making and in our confidence assessment, and verification and validation methodologies that meet the standards of in our case, the Nuclear Regulatory Commission. And so we're kind of looking, you know, in all three of these areas to continue to develop to get to the point where we would have a decision-making system that provides a decision, or a set of decisions, evidence for those potential decisions, and then a confidence to help all of that guide acceptance and usefulness of the decision maker. And so next slide. Thank you. Oh, and so so that was kind of what I wanted to share of what's going on at UT in the nuclear power plant world. And I'll be happy if anybody ever wants to reach out to discuss more. Please feel free to email me.
Okay, thanks so much, Jamie. And with these shorter talks, we really are not going to have time for Q&A, but if you type in questions and let us know who they're for, we'll try to forward them to the speakers. So thank you, Jamie. All right, our next speaker is Dr. Linyu Lin, sorry. And he is a postdoctoral research scholar in the Department of Nuclear Engineering at North Carolina State University. His research focuses on data-driven modeling and validation, predictive capability maturity quantification, digital twins, and autonomous control in advanced reactors. And Linyu is going to talk today about trustworthiness assessment of digital twins in NAMAC. Okay.
Thank you, Nancy. So today I'm going to talk about the importance of trustworthiness, and we're referring to the digital twin and the autonomous control, so-called NAMAC system, as a target application of trustworthy assessment for machine learning and artificial intelligence. So the goal of this presentation is to go through some of our challenges that we have met during the use of machine learning algorithms for the development of digital twins and the autonomous control system. Next slide, please. So the nearly autonomous management control system, so-called NAMAC system, is a comprehensive control system to assist the plant operations by furnishing recommendations to operator. And such recommendation is derived by integrating knowledge from the scenario-based model of the plant operating procedures, real-time measurement, and so on. So NAMAC is an intelligent operational software, but as previous presenter mentioned, the goal is not to replace human operator, but actually to try to make use as much and as broader knowledge as possible, especially during emergent and difficult situations. And to better extract and store the knowledge, NAMAC uses digital twin technology, where we're relying on the power of artificial intelligence and the machine learning in expressing these highly nonlinear behaviors and heterogeneous information during accident and also the nominal transients. So to maximize the extendability of the NAMAC system, the recommendations are derived from the hub of digital twins. And these digital twins have different functions for the intended use, and they are connected by a structured workflow. So if we look at the picture on the right, the diagnosis first reads the sensor data from the simulator and produce a complete picture of the reactor states. And based on that diagnosed information, we have the strategy inventory to identify all the available control actions. And then we also have the prognosis for doing the front-running predictions that evaluates the consequences and different actions and initiating events. So later, all these predictions are fed into the strategy assessments for deciding the optimum paths that could satisfy a specific goal and preference. Next slide, please. So this table summarizes the current implementation of different digital twins with different modeling approach. Some of them are implemented by machine learning algorithms. For example, the diagnosis digital twin, we're looking at the feed-forward network, recurrent network, and also the logic programming. And the selection of the different algorithms depends on the complexity of the case study and also a high-level requirements. For example, the strategy assessment, we are having both the limit surface approach, but also we're looking at the expected utility theory to account for the impact of uncertainty during the decision-making process. And here I want to emphasize the reason of having a hub of digital twin instead of just one single powerful digital twin is that we believe there is no one shoe fits all. Instead of having a super digital twin that could cover all the scenario, we're trying to have a hub of digital twin with different functions that could combine heterogeneous knowledge and that could interact with each other and with the environment. And this is because in a complex system like nuclear reactors, learning process is rarely one-time training, but rather a training through different disciplinaries and a variety of exercises. So by dividing a complex task into a list of subtasks, each digital twin could perform and interact with environments and their task. Meanwhile, the big data requirement on a full-scale and multi-physics system can be relieved to a separate scale and simplified system where data becomes more feasible. Next slide, please. To enable the confident use of digital twins, digital twins need to be adequately modeled for the intended use, where we're defining adequacy based on the digital twin's uncertainty and its impact on the target applications. So here we just have an example that we're dividing the digital twin uncertainty into 3 levels. In level 1, for example, the future scenario is clear with some uncertainty, and the digital twin thus should have fixed forms and parameters. And in this case, the digital twin can be used in high consequence system where decision making is fundamentally based on the digital twin. But as level goes higher, the scenario becomes unclear and the digital twin uncertainty also increases. In these cases, the consequences of our applicable targets for the digital twin gradually goes down. Next slide, please. So to identify the major source of uncertainty and also to avoid biases due to implicitness, we have been trying to design a digital twin development assessment process that aims to guide the refinement and improvement of digital twins. Currently, we're trying to adapt the evaluation model development assessment process in the regulatory guide 1.203 to the digital twin technology. And in this adapted framework, there are 5 elements, including the requirements, knowledge-based development, digital twin development, and also the digital twin assessment, and also the trustworthiness assessment. And the goal of this process is to have a scalable and robust application of digital twins to a generic type of use cases and also a generic type of reactors. And since this development assessment process is conducted iteratively until we have a reliable and trustworthy NAMAC, and among the refinements of all these 5 elements, we believe that the trustworthiness assessment is of the most important attributes especially on how we define and evaluate the trustworthiness, and how we could integrate different evidence from different sources. Next slide, please. So for model-based approach, the trustworthiness are clearly defined. It's also known as credibility. And in one of the technical approach, the credibility of model-based approach can be evaluated by 6 attributes. And if you look at the picture on the right, we can actually compare the achieved level and the target level for each attribute and have this kind of spider plot to determine whether the credibility of certain of this model is adequate. But for machine learning based method, the trustworthiness is not really completely defined. Some non-attributes could include accuracy, security, robustness, explainability, reliability, and so on. But for our case, our research is not to complete the list of trustworthiness attributes. Rather, we have been focusing on the integration of information from different sources and also heterogeneous type of data. So this is an ongoing research, and we have been trying to develop a framework based on the assurance case that aims to justify if digital twins is acceptably mature in a structured argument. And this picture on the right-hand side shows a graphical representation of an argument process towards the trustworthiness of a digital twin based on evidence in data coverage, algorithm verification, validation, and also the uncertainty quantification. So currently, we learned that the trustworthiness assessment process, the quality of evidence could have significant impact on the target trustworthiness and needs to be evaluated. And such quality could refer to the relevancy, uncertainty, and also the scaling of training and testing cases to the target application. We also learned that during the evidence integration process, the complex relations, priorities, and trade-off between different attributes of trustworthiness also need to be considered. At last, as Professor Jamie Coble mentioned in previous presentation, considering the real-time nature of digital twins, the trustworthiness also need to be quantified, automated, and conducted in real time. For example, it can be for deviation detection and also for discrepancy checking purpose. So this is all my presentations. Please feel free to ask or contact me if you have any questions. Thank you.
Thank you, Linyu. Wonderful presentation. So,
Thank you.
Okay. All right, so moving on to the next presentation. We have Chithuri Wickramasinghe and Dan Marino, who are both PhD students at Virginia Commonwealth University. They are both working on developing systematic approaches to increase human trust in artificial intelligence. The title of their talk is Trustworthy AI Development Guidelines for Human System Interactions. And I will let you take it away.
Hi everyone, we are going to talk about Trustworthy AI Development Guideline, mainly focusing on how to improve the human system interactions. Next slide, please. As we all aware, artificial intelligence is influencing almost all areas of human lives. However, still humans have hesitant to deploy and use these AI systems, mainly because as humans, it's difficult for us to understand the internal decision-making process of these AI systems. So Trustworthy AI research area has been introduced by addressing this problem. It is a diverse research area where it includes a lot of areas such as explainability, accountability, verifiability, sustainability, transparency of AI systems. So in this presentation, we are going to talk about two things. First is guidelines for building human trust to improve the interactions between human and AI systems. And then we are going to provide concepts of trustworthy AI and one example towards achieving trustworthy AI. Next slide, please. So when you look at the human system interactions, it is mainly focusing on research area, designing development, and research on effective interactions between human and intelligent systems. This interaction can happen through various mediums such as natural languages, haptics, or graphical user interfaces. When looking at the AI development cycle, you can identify three main actors who communicate with each other. That are AI system itself, system developers, and system users. So what we are trying to do is we are look into these interactions and how we can incorporate trustworthy AI into these interactions. Next slide, please. So in different entities follow different AI life cycle based on their requirement of the given system. However, all of them have common phases and specific tasks which are presented in here. It is important to identify the life cycle and its tasks to identify what are the entities interact with each other in each of these phases. Next slide, please. So in here we presented what are the three interaction type that we identified and in which phases this interaction take place mostly. For example, AI system and the developers mainly communicate with each other during development phase, testing, implementation, deployment, and optimization phases, whereas developers and users mainly interact with project initiation phase, concept development, and optimization phases. Next slide, please. So when you look at the trustworthy AI, many academic and non-academic organizations such as IBM, European Commission, Department of Defense, they have different definitions to a trustworthy AI. However, all of them talk about ethical principles together with formal AI verification techniques in order to define this trustworthy AI with the common goal of allowing people and societies to develop, use, design this AI system without fear. One such organization, which is high-level expert group for artificial intelligence, they has taken the first step towards developing a benchmark framework for trustworthy AI system, and I have below given this the definition as well. Next slide, please. So United States, together with Organization for Economic Cooperation and Development, has identified these 5 principles as complementary principles toward achieving trustworthy AI. First one is inclusive growth, sustainable development, and well-being, which focuses on developing AI systems to benefit human and the planet, also not harming the natural environment while ensuring the well-being of present and future generations. And the second principle is human-centered values and fairness, where it focuses on developing AI system which respect laws, human rights, diversity, and democratic values. The third principle is transparency and explainability, where it focuses on development of AI systems which should be able to provide some transparency of their internal decision-making process to the users. The fourth one is robustness, security, and safety, where it focuses on development of AI systems which are secure, so robust, and safe throughout its life cycle. And the fifth principle is accountability, where all actors who involved in designing, development, and deployment of this AI system should be accountable for proper functioning of these AI systems. Next slide, please. In here, we have identified a few guidelines which should be implemented through the 3 different interactions that we talked before. We will look into it one by one. Next slide, please. The first one is interaction between the AI system and the developers. As Matt talks about, the global interpretability and local interpretability, which are 2 main things that developers should mainly focus on, because that allows developers to analyze the AI system and check whether it provides right outcomes for right reason and identify where the AI systems can go wrong. It allows developers to fix defects of the developed AI system and to improve their trust before deployment of this AI system in the real world. And also interactive visualizations are important in order to explore hidden patterns or model behaviors so that developers can take necessary actions to fix and explore AI models more. And the fourth one is anomaly detection mechanisms. It is important to incorporate anomaly detection mechanisms for these AI systems, mainly to identify abnormal scenarios which can happen due to data creeps or some kind of attack activities. It allows developers to update the AI system and protect them from harmful interactions. Next slide, please. And the second interaction type is interaction between the AI system and the system user. Local interpretability or providing explanation for specific user input is important because it improves the user trust on the AI system, and it gives user to evaluate whether the AI system gives correct decisions. So further, it gives us a feedback loop so that developer can improve if there is something wrong with this developed system. And also interactive visualizations are important. They should provide wide range of interactive visualization covering a large variety of users, for example, depending on age, gender, disabilities, etc. And also these developed systems should be able to provide an outcome within reasonable amount of time. Also, they should consider diversity, non-group discrimination, and fairness. These developed AI systems should not have bias towards certain group of people based on their age, gender, disabilities. Next slide, please. And the final interaction type is interaction between developers and users. This is mainly important because it is important to identify what kind of interaction can happen during AI lifecycle and which data that should be transferred between these two groups and the lifespan of this data and who has access to which data and things like that. So it allows us to incorporate privacy and data governance rules and also to standardize the process of this AI lifecycle. Next slide, please. And finally, we identified that developing trust or incorporating trust into this AI system is context dependent. For example, a loan approval system, they might prefer linguistic explanation. However, for robot teleoperation, in that kind of scenarios, it is important to give something like haptic feedbacks or something that can use more efficiently. Also, it is important to define a global framework for trustworthy AI with new qualitative and quantitative measures so that researchers can compare and verify this AI system by following a common ground. And finally, we think that AI augmentation can use as a way to achieve trustworthy AI because it allows human and AI systems to work together to make a final decision. Next slide, please.
Okay, so now we want to talk a little bit about some work that we are doing here at VCU with AI augmentation. So what we are exploring in here is how to use AI augmentation as a path forward to trustworthy AI. And in this particular example, we present a case scenario for augmented robot teleoperation. Next slide, please. So the motivation behind this is, well, as we have been talking about, is that despite the performance of AI systems, some sectors hesitate to adopt AI because of lack of trust in these systems. So our thesis is that to use AI augmentation as a path forward to build trustworthy AI. And the reason for this is that augmentation provides a preferred alternative or complete automation because basically instead of replacing humans, AI augmentation uses AI to improve and support human operations. creating an environment where both can work side by side. So in this small talk, what we present are some guidelines and motivations for the development of AI augmentation, specifically for robot teleoperation, and we show some work that we have starting to do here at VCU and with SICAM to design a robot teleoperation testbed to explore these ideas. Next slide, please. So we start by presenting a definition of trust. So, well, there are many definitions, but we like this one for the purpose of our discussion, which is predictable behavior, even in the presence of uncertainty. And we like this idea of splitting trust into two components, which is intentions and competence. And we can see that with this split, we can also, like the trustworthy AI principles that we mentioned before, from the OECD can be grouped together as an intention and competence. So here, for example, competence can be robustness, security, and safety, while intention is accountability, transparency, human-centered values, and inclusive growth. Next slide, please. So the approach that we are exploring here is to use AI augmentation as a path forward to trustworthy AI. So the idea is that we can, with AI augmentation, we can split tasks between AI and humans, where high-risk decisions with high uncertainty are given to humans, while the AI takes care of simpler tasks. So with this framework, we can alleviate a little bit the shortcomings of AI by maintaining accountability in humans. This framework of shared autonomy also provides an environment where AI can take increasing responsibility proportional to the improvements of robustness. So basically, we can use AI augmentation like a dial, where depending on where we can choose how much the AI gets involved depending on the difficulty and the impact of the task. With the idea that we always maintain accountability in humans, and high-level tasks are like the intention of the task is always given by the human. And this also opens the door to start building the AI, because, well, right now there is a lot of shortcomings in terms of robustness and intention, as we talked before, and transparency. So the idea of this is that we can start introducing these technologies gradually, while the technologies are improved in terms of robustness and transparency. Next slide, please. So in here, the idea is we want to work on robot teleoperation. Sorry, can you do? I think this. Yeah, thank you. So the idea here is that robot teleoperation provides an environment to study human-machine interactions, and it has shared autonomy embedded in the field. So we like it as a case study because we can use it to explore these ideas, as there is a tight interaction between humans and machine. So the objective that we're exploring is create like an AI augmentation blocks, which takes input from multiple sensors to perform a commanded action with high success rate. And the AI will combine data from several sources in order to have a complete representation of the system. So again, the idea here is that the human gives an input, and well, that commands a desired input, and the AI takes care of executing the task with high success rate. And next slide, please. So this is a test bed that we created to explore this approach. It's basically like a robot manipulator. We have also an input device, which is kind of like a puppet, like it's mimicking the manipulator, and it gives like a way to command the robot. And with the robot, we have we have put in place many different kind of sensors, like force sensors, cameras, point cloud cameras, microphones, to obtain data and build this AI augmentation block. Next slide, please. We also use the idea is to, well, we are developing this block using augmented reality, and the idea is to superimpose virtual objects in the scene to provide improve situational awareness, and also explore some ideas of how to create an effective interface between human and machine. Next slide, please. And these are some of the guidelines that we are considering for the development of this system, which is the first one is basically the human should retain control and has to engage in the task at hand actively. The AI actions will only act as a recommendation or enhancement of human actions. The second one is that is fundamental to ensure robustness, and it's necessary that the AI is aware of situations where there is not enough information to act autonomously. So it is really important to assess uncertainty, and in the presence of uncertainty, there should be a clear behavior of the AI, which should be to increase the care or communicate to the operator that well, right now there is not enough information to act accordingly. So this is very important because, as we talked before, one of the ideas of trust is that the user should be able to understand, to trust the system even in the presence of uncertainty. So there should be a clear behavior even when the system doesn't have enough information to act. Well, I think that, yeah, we are running a little bit short on time. So next slide, just to conclude. Well, here basically we are presenting AI augmentation as a way to build trustworthy AI systems, and we are looking at augmented teleoperation to explore these ideas and to create a test bed to develop these systems. Next slide, please. Thank you. So these are some of the papers that that showcase these ideas. And
okay.
Yeah.
Thank you, Daniel and Chituri. Appreciate you joining us today.
Thank you.
All right, our next speaker is Dr. Rick Villa. He manages the Plant Analysis and Controls and Sensors Department in the Nuclear Science and Engineering Division at Argonne National Lab. He has ongoing research projects involving control system design, modeling and simulation of nuclear systems, the operation of advanced nuclear reactors employing load following and load leveling using energy storage, and artificial intelligence and machine learning for plant performance improvement. The title of Rick's talk is Improving the Explainability of AI Through Inclusion of Process Information and Automated Reasoning. Hey, Rick.
Thank you, Nancy. Good afternoon, good morning, everybody. So we have a number of projects going on in our Nuclear Engineering Science Division that involve AI. It's 7 or 8, I've lost count. Some of those, in fact, 4 of them are RP Gemini Awards, which tend to be a little more abstract, conceptual. You know, it's AI ML for improving monitoring and control of power plants. Since this symposium, you know, this 4th edition is aimed at explainability, I'm going to revert to the projects that involve utilities that we're working with. And we're working with 3 utilities. And the idea here is monitoring. You know, the utility engineer needs to, you know, observe the system, have a situational awareness of what's going on. And we're looking at how that person does that. If there's an anomaly in the system, there's information they process, not only the sensor information, but you know, once they've identified the component, perhaps they're looking at how that component is connected to other components. how the component is controlled. There's just information in addition to sensors. And that person actually works through a reasoning process to come up with what's wrong. If there's a tank level that's going down and the flow is going up, maybe it's a leak. So those sort of qualitative reasoning processes we're trying to approximate. Essentially what we're trying to do is replicate how the human works in these power plants. And if you can replicate how the human diagnoses things, then you're in a much better position to explain what actually went wrong, because you're thinking in that person's framework already. Next slide. So I will say in the industry, the nuke industry, as Jamie Coble mentioned, we're still pretty back in the Stone Age. We're data-driven machine learning approaches, but at the research level, we're trying to move things forward. So, Argonne was involved in the early days of ML in power plants. The first AI applications were data-driven, as I mentioned, and out of Argonne came the multivariate state estimation technique in the 1990s. It was basically for sensor fault detection. And yet today, things are still data-driven. I mean, we have cluster-based techniques, PRISM, but it's still basically pure data-driven. No information other than sensor values are being brought in. Well, that's attractive from a application standpoint because it's one size fits all. I mean, it doesn't. If you don't need to know about the system you're monitoring other than the sensors, then you can put this on anything. But then you fall victim to the fact that you're, and you've seen these words before, shallow. You don't have any understanding of what's going on in the system because it's just sensors. There's no physics. It's opaque. You don't really know how it got to the diagnosis, and it's brittle because if you go outside the training range, you break. So we're trying to overcome those disadvantages. So the work that's taking place at Argonne now is trying to incorporate domain knowledge into this diagnostic process. And basically what the domain knowledge is, it serves to constrain your solution space. Just fewer degrees of freedom, so you can't wander around quite as much in the decision process because you're anchored to physical reality. And that might be conservation laws, it could be constitutive equations, basically physics-based type information. So over on the right-hand side, I've just compared from a plus-minus standpoint, the data-driven techniques against physics-based. I have a number of metrics there. I'm not going to go through them, but there are some real advantages to incorporating this physics information. Next slide. So we really need to improve the business case if we're going to have widespread AI. And by AI, machine learning, data-driven, that's one subset of AI, but we're looking to get bigger than just machine learning. We're looking to bring in, as I say, process information, replicate the operator's reasoning process. But if we're going to do that, and we're going to have a good business case, we got to do a couple of things. First of all, we've got to have an acceptable level of dependence on the subject matter expert. I mean, we can't have on each application, some process modeler creating a one-off for the particular system that's being understood. Or and we basically need to get the physics information into the methods in the software. I mean, utilities long ago dispensed with plant system modelers. I mean, nobody runs retran at power plants anymore. It's all farmed out. So we've somehow got to take what in the past has been expertise in subject matter, disciplines at power plants. We got to bring that over and get it into the methods and the software. Instead of that being communicated by the plant specialists to the software. We just need to embed it in the software. So we need that acceptable level of SME involvement. We need to be explainable. We've got to understand the underlying reasons process. We got to understand how you know, the answer was arrived at. The human should be able to easily decipher what the machine is telling the person. Specify a level of granularity. I mean, if you have one thermocouple in a power plant, you're not going to be able to say too much. I mean, presumably, if you're trying to do diagnostics, there are certain things you want to do, certain requirements for what you want to diagnose. So that's going to require a supporting sensor set. So one needs to be able to first state the requirements of what you're trying to determine, and then from that infer what sensor set will give that to you. And you don't want to be over-determined necessarily on the sensor set if it dramatically affects cost. But a certain degree of over-determination is good in terms of reliability, and I won't go there right now. And we need to have quantifiable reliability. You need to know what the uncertainty is. I mean, you're never going to have a perfect sensor set. There's always going to be some ambiguity, and you need to be able to express that ambiguity, and we do it through probabilities. Next slide. So what I'm going to do now is work through those 4 areas for getting a good business case model, and I'm going to do it by an example that we have going on with a couple of utilities. So we're trying to, as I say, minimize the dependency on the subject matter expert. So here we have a feed water system in a light water reactor, and we're trying to diagnose faults. So on the left-hand side is the PID for that system, and of course the engineer responsible for that system has that available to him. We take that PID and we encode it into a network diagram, which is the center figure there. And then we take that diagram and we encode it in a text-based file. So now we have basically the connections among components of how mass and energy flows embedded in a model. And so this is the sort of thing that the engineer has in his head, although ours is a little bit better in the sense that it's quantitative. I mean, you can actually assign numbers to mass and flow. The operator will tend to think qualitatively, think in terms of trends, increasing, decreasing. So that through this digital twin, we're incorporating what in the past the SME has brought along. Next slide. So the high explainability, we're trying to replicate, as I say, how the operator thinks. And so to get the diagnosis, we do something called forward chaining. It basically takes evidence and tries to come up with causality. I mean, and so here we have the digital twin, we have the sensor measurements, and we process those to determine what happened. So that's fine. The computer's happy, but the operator isn't happy yet because he doesn't know necessarily how that answer was arrived at. So we can go the reverse direction through backward chaining, and that's where we make the answer explainable to the operator. We basically go backwards through the forward chaining, and that's our explainability component. I will say that we've gone a long way in the forward chaining. The backward chaining is something we're working on. I know the utilities are looking for that. They need something that's actionable. So that right now is a research area that we're pursuing. Next slide. So in terms of granularity, there is a default sensor set in these plants. And so far, we're just working with, or I should say in the utility domain, we're working with existing plants. So here again is the high pressure feed water system. And so the oval shaded area on the left there, a couple of first point feed water heaters, and they're equipped with sensors. And if you want to be able to diagnose any of those faults shown on the right-hand side in those 2 tables, there are sufficient sensors to do that. And so we actually have a program that operates as an outer layer around our software that you would, I'm going at this a little backwards. I mean, you would input to the software those events shown on the right-hand side, and it would tell you what the requisite sensor set would be. So in other words, to diagnose those faults shown on the right-hand side, you would need the sensors that are shown in the oval over on the left-hand side. Okay, next slide. So I mentioned reliability. So we do this in terms of uncertainty and probability. And so continuing on with that feed water example, I've failed a sensor, the arrow points to it there. If you run our diagnostic algorithm through this, it will tell you there's 4 things that have equal probability of explaining the sensor sets, the diagnostics that are observed. So again, the sensor set will only provide you with a certain amount of information. But you need to be able to understand what the limitations of the sensor set are. So here's an example of.
Hey, Rick, we need to wrap this one up. Sorry.
Yeah, this is the last slide. Next slide.
Okay.
So some of the challenges, you got to identify the requisite sensor set. Some of these things that are going on in the plant aren't directly measurable, degradation mechanisms. You need virtual sensors. We really need a comprehensive policy for data formatting, curation, archiving. I've yet to see this in any of the utilities that we're dealing with. That concludes the presentation.
Okay, thank you so much. All right, our next talk up is Dr. Ross Kuntz. Ross is a data scientist with the Transient Kinetic Analysis Group in the Energy and Environment Science and Technology Directorate at INL. His work, which focuses on developing an understanding of how and why a catalyst works, is integral in developing advanced, efficient catalysts. And the title of Ross's talk is Exploring Reaction Mechanisms with Explainable AI. Hey, Ross.
Okay, thanks, Nancy. Appreciate it. So again, thanks, Nancy. Appreciate all of that intro. I'm going to be talking about the explainable AI methods, and first and foremost, I'd like to, say thank you for all my collaborators' work in this kind of process. So go ahead and go next. So we heard a lot of talk about, explainable AI between, using machine learning or AI, and then also kind of what's the ground truth, right? And so, with machine learning or AI, we want to take something that's hard to predict, some sort of response that's hard to get at or hard to measure, and we want to predict it with something that's, easily quantifiable. And then with physics-based approaches, we actually want to take, a set of governing rules and then apply some sort of fixed assumptions and try to validate that against some sort of experimental data. And so this kind of approach kind of blends the two, kind of creating this explainable AI technique where we're using data-driven techniques and then looking at the physics and figuring out where AI or ML can actually apply to the physics to make sure that when we're generating these, hard to predict quantities or predictions, we're actually showing, oh, this is the underlying physics that how we got there, such that, we're explaining how we got to a certain point. And so as a quick example, on the right-hand side is a set of elementary steps. So each different numbered value is going to be a given mechanism, and each different line is a separate elementary step. And so this is kind of like the chemical process of, say, N2O decomposition, where you might have different mechanisms at play. And so our goal here is to go ahead and try to figure out directly from the data what is the best set of elementary steps, and also what are the rates associated with each individual step. So how fast does N2O go to nitrogen and then oxygen on the surface and things like that. In this case, we're going to use temporal analysis products reactor. So the reason why is that we've got a high degree amount of data, as well as the physics are quite unique to this reactor, such that we can actually distinguish the transport and reaction and get into some of the chemical measurements. So let's get into that. Let's go to the next slide. So based on the physics of what's going on in a tap reactor, this outlet response that we actually get can be separated into gas concentrations and reaction rates per, this reactant hitting this catalyst zone and forming all these different products, right? We can also get the surface concentrations through this integral of the rate. So what we're trying to do now is say, okay, given this green table at the bottom, we've got a set of elementary steps, found in common chemistry books. We can relate that to a set rate expression. And from that information, we can also turn this into a linear form. once we hit that linear form, this is jackpot for, you know, statisticians or machine learning or AI, because now this is something where we can actually start applying our algorithms. The interesting case with respect to the physics is that all this relates to a linear model with all these different gas concentrations and surface concentration reactions. And so the idea for machine learning now is that we actually have all these different measured quantities. Now we actually want to do inference and start looking at this these beta at the bottom of this equation, where we have these intrinsic kinetic coefficients, start estimating those appropriately through machine learning, as well as kind of remove some of these variables such that we actually get the correct elementary step that we're looking for. So in this case, we're going to be applying a lot of variable selection machine learning tied in with the exact physics to describe the system. So go ahead and go to the next slide, please. So in our results, just very briefly, right, we're taking that large equation, well, not very large equation, but all these different gas concentration interactions with our surface of the catalyst and building out a large linear model. And what we want to do again is do some variable selection using machine learning to down select which one of these interactions are important for the mechanism and the elementary step, as well as describe these coefficients, these beta coefficients, describe the actual chemistry, the kinetics, right, these kinetic rates. And so doing this type of approach using, say, non-convex penalization, if anyone's out there familiar with SCAD, smoothly clipped absolute deviation, we use that on the regression model for each individual elementary response to actually get the estimation of the number of active sites and intrinsic kinetic coefficients with different gas species, as well as actually remove the effects that aren't necessary in the model describing a system. And then also looking at the correlation structure on the right-hand side to actually determine in what cases, if we looked at correlations between reactants and products, where we'd actually find a specific mechanism, for example, either Idel or Langwood-Henshaw would, as well as where the bounds on those different forward or reverse rate coefficients exist within a complex system. So go ahead and next slide, please. So very quickly, I think the graph on the right kind of sums it up in generic sense. What we want to do is we want to take those hard to reach problems where we have a set of physics, say parameters or variables, right, that we want to describe with experimental data. So on the top of the tree here, we have experimental data, and one of the subset would be TAP data, right? And we actually want to start deriving what's happening with the physics, right? And that's going to be through a series of, say, machine learning techniques tied to the physics, and finally going down to surface chemistries, and then finally down to specific quantities used in, say, density functional theory that describe a system. And so in this process, we want to start connecting, you know, where can machine learning apply to the physics such that we can get this optimization through a data-driven fashion, right? And so that way we don't actually have to say to the user, we got these predictions of these quantities or intrinsic kinetic coefficients, but we don't know how. We can come back and say, oh, well, based off of the physics, this is how we got these different quantities or estimates, right? And so we've got plenty of different challenges ahead of us, right? And so no work is always complete. We're looking at, you know, different structures of machine learning algorithms, not just to detect whether something exists in relationships, but also the correlation structure between elementary steps such that you can actually describe the complete system or the complete reaction mechanism. And then we'll also want to develop like key indicators for like changes in mechanism or changes in active sites. We want to start linking the structural characterization to the kinetic characterization via TAP, right? So kinetics are only part of it, but we also need to look at the structure of the material, and having that integration will give us a larger picture about what's actually happening to the catalyst, such that we can actually generate new catalysts in the future. And finally, we want to get all the way down to that root of that tree by developing, you know, links directly from data all the way down to like very basic transition states in, say, density functional theory and things like that, and pure physics approaches. So go ahead, next slide. And with that, I'd like to acknowledge DOE and Advanced Manufacturing for giving this opportunity, and group members at INL. Thanks.
Thank you, Ross. Excellent talk. Okay, so our final speaker for the day is Dr. Akshay Dave, who is a research scientist working at the MIT Nuclear Reactor Laboratory. He's been there since the fall of 2016. His research interests encompass applications of machine learning methods towards solving nuclear engineering problems, thermal hydraulic safety analyses, novel experimental facilities that operate at extreme conditions, and high fidelity, high resolution experimental characterization. So the title of Akshay's talk is Integration of Neural Networks in Control of a Subcritical Facility, Current Progress and Opportunities. Okay, Akshay.
Great, thank you, Nancy. Thanks for the introduction. And my talk will be focused on a project undergoing in our group. And our group is interested in working towards pushing forward the current state of the art in terms of employing machine learning methods for autonomous control. And this current work actually tries to bridge the gap between code and plant. And next slide, please. Thanks. So I'll start with going briefly through the motivation for autonomous control. And I think Jamie hit on this in our slides already. And the current large economic woe for nuclear power plants is the large upfront capital costs and also the day-to-day O&M costs. So for the large upfront capital costs, we have had a lot of interest and investment in developing smaller modular reactors. But currently, it's unknown whether or not the O&M costs will scale down in proportion to the unit power. Next, please. So there is a lot of focus on developing alternative methods to reduce these costs and autonomous control, either semi-autonomous or fully autonomous control, or automating some other parts of the rest of the plant management is of interest. However, as you can see from the picture on the bottom right-hand side corner, the current paradigm in terms of controlling the reactor still involves human operators. And research in autonomous control has been mostly isolated in universities or labs. Next, please. And we do have a need for automation for reducing costs for smaller modular reactors as well as microreactors. There is a need for deep space exploration. And there's also an opportunity for the current fleet to benefit from some of this work in terms of automating some of the non-control related tasks, such as automated radioactive waste management. So next slide, please. So on this slide, thanks. So on this slide, I would like to I would like to just provide a brief overview of the current state of the art in nuclear power plant control using graphs rather than talking through text. And so the figures you see in the middle here are taken from a recent paper that focuses on using reinforcement learning to provide automated control of a PWR, a digital twin of a PWR. And in this paper, they actually control 4 different major systems shown in the bottom middle figure. And their main goal was to see if they can use reinforcement learning to increase power from 2% to 100% power, shown by the figure in the middle top. So I actually think these results were very exciting, and partial results are shown on the right-hand side figure, where they've been able to use reinforcement learning to actually have control over these systems. And the interesting thing here is that the control is non-discrete. So unlike some of the games like AlphaGo, where actions are discrete, for nuclear systems, you actually have a variable amount of control, which you can see, for example, for the control rod banks on the bottom right-hand side figure. So if you contrast the top 2 figures from what they were expecting and what they achieved, there's still a lot of work to be done. But in my mind, the algorithm is actually piecewise mature, and we need further refinement. But I think the big question now is, how do we work towards shifting from results on code and working towards implementing these algorithms to very complicated facilities like PWRs. So next slide, please. So in our group, the answer that we have proposed, or at least a step towards addressing this answer, is what we call the MIT graphite exponential pile, which is a subcritical facility shown in the center figure here. So the graphite exponential pile is a facility with graphite blocks, which has about 1,300 natural uranium slugs. It's a 90-inch cube. And if you place a neutron source at the bottom pedestal, which is the bottom part of the graphite pile, you achieve some neutron flux distribution. So our overall objective has been to design and construct an experimental facility that can demonstrate some sort of machine learning-led control or manipulation of the flux within the pile. So this bottom figure on the left shows our preliminary design, and then the animation at the top right-hand corner shows the in-pile facility that we have created to fit into this 3.5-inch square inch hole that runs through the entire facility. And in this way, we're actually able to both monitor and perturb the flux spatially and temporarily. So using helium-3 neutron detectors, we're actually able to monitor the flux. And our idea is to have some, since it's a subcritical facility, you would have one side of the pile which acts as an unknown perturbed zone, and the right-hand side of the facility as a control zone. And using several neural networks, we're actually able to have some sort of competing actions being taken on one side of the pile, and then a response on the other side of the pile. And throughout our work so far, we have actually been able to develop a open source neural network library that provides multidimensional regression for not only subcritical systems, but critical systems like the MIT reactor as well. So next slide. Okay, so now I would like to pivot towards discussing my views for how we could use XAI and incorporate into the overall autonomous control frameworks that I think several groups are developing. And I think the previous speakers have touched upon the details, and especially Matt went through the details of XAI. But what I would like to highlight is this figure on the top shows a very interesting juxtaposition of the explainable model box and the explanation interface. And I think actually this is probably the most important part when it comes to a technical implementation of XAI methods. I think that we need to focus on developing tight coupling between both machine learning methods and XAI methods that are context aware. And what I mean by that is within machine learning, we have several types of problems, for example, regression, time series forecasting, or RL control. And for our particular context, for nuclear power plants, we need to develop a framework that can address these problems in the context of having XAI output specifically for our industry. And finally, I think Rick Willem had touched upon this, but the main goal of XAI really is to see end user traction, and for nuclear power plants those are actually operators that are overseeing possibly these RL control systems. So to address this, on the bottom right-hand side, I have suggested development of an integrated XAI framework. And the basic idea of this is shown on the bottom right-hand side of this slide, where we have data, from simulation, from our conventional tools, but we also have physical data that is incorporated in training the machine learning modules. But instead of conventionally just developing machine learning methods isolated on its own, we would have a concurrent or asynchronous development of an XAI module that is taking an end-to-end approach instead of just a post-processed approach for interpreting the data. So for this, I think there's a really good opportunity for us in the industry to have some cross-collaboration through open source development, because an improvement here will, the underlying improvement for all of these modules will have an impact on all reactor types. And I also think that again, to reiterate, we need to assess human factors as end users and not machine learning experts. And for this, my suggestion would be a starting point could be collaboration with the research reactors, where we would have more flexibility over obtaining offline data, as well as finely tuning methods in assessing the human factors. Next slide, please. So, this is my final slide. So I'd like to talk about opportunities. I think that facilities like the graphite pile have a really interesting place in terms of the fact that it is inherently safe and possesses no safety criticality risk. It gives us a lot of opportunity to allow machine learning models, which we may not know the eventual or nonlinear outcome of, and place that and get experimental data out of, and to provide this sort of access. Next click, please. To provide this sort of access, our plan is to eventually allow remote uploading, allow students or researchers or engineers to remotely upload and train their methods on our facility without incurring any criticality safety risk. And we are also trying to open source a lot of our development. We have published our software that we're using to build the neural networks online already. We will also be eventually publishing our experimental data, our neutronics models that we're using for the graphite pile, as well as the control system framework itself. And with that, thank you.
I thank you, Akshay, and all of our wonderful speakers today. We had a total of 7 presentations with 8 presenters, and thank you all for very informative, very interesting talks. We had 5 talks on explainable AI, 2 on trustworthy AI, and you can see how some of these they're bridging those topics from understanding the AI process and how we do use machine learning in particular and how we translate that back to the users, and then also how we're actually applying some of these things for applications like control. So some very interesting work there. I'm excited by this talk. I'd like to tell everybody to pencil in June. I'm not sure that we have the exact date nailed down yet for the AI ML Symposium 5.0. And we are also still refining our topic. As you see, as we go along, we start getting more and more specialized in these things, but you'll see that these topics don't become any less relevant. Just because you're working on a nuclear control system doesn't mean you can overlook the trustworthy or the explainable aspect of AI. So thank you very much, everyone, for your attendance. We had over 200 people throughout the session, and attendance stayed pretty steady. I think that represents a strong interest in this topic. And again, we've recorded this. We'll make this available at a later date. And thank you all. Have a good rest of your day. Bye. And thanks, Nancy, also, of course, goes without saying, especially Nancy for emceeing this event. Thanks.